Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 4 today, and we're looking at Section 4.2, which is probability rules for more than one event. Many situations involve two or more events that intersect with each other. A contingency table can be used to show the number of occurrences of events that are classified according to two categorical variables. So here's an example. We're going to use the contingency table to calculate the probability of events A and B, where event A is a student living in the dorm being a female, and event B is a student living in the dorm being a freshman. So you can read this table. We have all of these students divided up into categories, 17 female freshmen, 12 male freshmen, 7 female sophomores, 5 male sophomores, and so on. And then when you get to these so-called marginal numbers, which are the totals, it shows that there are 28 females, 22 males, for a total of 50 students. And those 50 students are also divided up into 29 freshmen, 12 sophomores, 6 juniors, and 3 seniors. So if you want to know the probability of event A, a student living in the dorm being a female, the number of females is 28, and the total number of students, I just noticed a typo here, is 50, not 52. Okay, but that decimal is correct. 28 over 50 is 0.56. All right, and then event B, a student living in the dorm being a freshman. There are 29 freshmen, and again, a total of 50 students. So the probability of B is 29 over 50, which is 0.58. Marginal probability is another term used for simple probability in the margins, or row and column totals, of a contingency table. Okay, let's get rid of that. All right, let's talk about the intersection. The intersection of events A and B represents the number of instances in which events A and B occur at the same time. And let's see, sorry, I got something in my way here. The probability of the intersection of two events is known as a joint probability. So now we want to find the probability that a student will be a female and a freshman, which is the intersection of events A and B. The number of students that meet the criteria is the intersection of the freshman column and the female, they have that backwards, the freshman row and the female column. So the probability of A intersect B is 17 over 50, which is 0.34. Then we have the union. The union of events A and B represents the number of instances where either event A or B occur, or both events occur. So in math, the word or almost always means and or, one or the other or both. If we don't want it to mean that, we have to say one or the other, but not both. All right, so you can see here, this is called a Venn diagram. And the entire colored area represents A union B. So using the same events, we'll find the probability that a student is a female or a freshman. So you see how they did this. There are 17 female freshmen, 12 male freshmen, so those are all the freshmen. And then you have also all these other females. All right, so if you add these 5 numbers together, 12 plus 17 is 29, plus 7 is 36, plus 2 is 38, plus 2 is 40. The probability of A union B is 40 over 50, which is 0.8. So there is a shorter way to do that problem, which is called the addition rule for probabilities. That's used to calculate the probability of the union of events, which is the probability that event A or event B or both events occur. Now, there is a special situation that can occur with the union of two events. Two events are called mutually exclusive if they cannot occur at the same time during the experiment. So in terms of the experiment that we're doing now, think the probability that the student is a freshman or a sophomore. All right, a student can't be both of those things. Okay, so the Venn diagram for freshmen and sophomores would look like this, but the Venn diagram for freshmen and females would have to look like this because they do overlap. For mutually exclusive events only, the addition rule states that the probability of two events occurring is simply the sum of their individual probabilities. Now, I want to caution you again, this is only when the events are mutually exclusive. In that case, the probability of A or B is just the probability of A plus the probability of B. Now, I take a little bit of issue with what they say here. What they say here is correct. But it's actually not necessary to say this. This formula here will work all the time, even if the events are mutually exclusive. So I like to joke that if you're going to be stuck on a desert island and you can only bring one of these formulas, you should definitely bring this one, okay? Because if the two events do happen to be mutually exclusive, then the probability of A and B will be 0, and it'll do the same thing that this formula does, okay? All right, so we know this formula will always work, and it says the probability of A or B equals the probability of A plus the probability of B minus the probability of A intersect B. All right, so let's see, calculate the probability that a student is, oh, this is a new example. Calculate the probability that a student either earned an A or is female. All right, so you see a new contingency table here. 9 students earned A's, 12 earned B's, and 4 earned C's. And there are 10 women and 15 men. All right, so if we want to find the probability of A or B, using that formula, we'll do the probability of A plus the probability of B minus the probability of the intersection. Now, if you think about how they did that last example, what they did basically was they just added, you know, if they were using these numbers, it would have been like they added 6 plus 3 plus 4 plus 0, okay? Now, if you just did probability of A plus probability of B, you would do 10 over 25 plus 9 over 25, but you can't just leave it at that because in that case, the 6 would have been counted twice. So because the 6 has been counted twice, we have to take it out once. That's the idea behind this formula. So we got 9 25ths plus 10 25ths minus 6 25ths, which is 13 25ths, which is 0.52. Notice that's the same answer you would have gotten if you had done 6 plus 3 plus 4 plus 0. It's just, I think this is a little faster. All right. Here is a Venn diagram illustration of the addition rule. The probability of A or B. You take the probability of A plus the probability of B. Now, what's happened after you have added the probability of A plus the probability of B, see A is here. I'm just going to put a little tick mark there. And then you add the probability of B. B is here, and it's also here. So again, if we just leave it at that, then the intersection gets counted twice. We don't want to count it twice, so by subtracting probability A and B, we take it out once. Okay. All right. Let's see. Get rid of my scribbles there. All right, that brings us to conditional probability. Conditional probability is the probability of event A occurring given the condition that event B has occurred. All right, so we're looking at math SAT scores with and without a prep class. 70 students took the prep class, 180 did not. And we're also told that 61 students scored 201 to 400, 147 scored 401 to 600, and 42 students scored 601 to 800. So if we wanted to find the probability of A given B, which is the probability that the student scored 601 to 800, given that they completed the prep class, all right, well, what you can do is just think of your entire sample space as being just the students who completed the prep class. So forget about everybody else. And out of those 70 students, 22 of them scored 601 to 800. So the probability of A given B would be 22 over 70, which is about 0.314. Now, if we just found the probability of A, the probability that a student scored 601 to 800, that's called a prior probability. It's determined without any additional information that could influence the event. So notice that the probability of A is 42 students scored 601 to 800 out of 250 students total. 42 out of 250 comes out to 0.168. So notice that the probability of scoring over 600, let's just say, goes up. It almost doubles if you complete the prep class. So taking the prep class definitely influences your chances of scoring over 600. All right, so here's another way to calculate conditional probability. The probability of A given B is equal to the probability of A intersect B divided by the probability of B. And then sometimes you'll also want to find the probability of B given A. So if you just switch all the A's and B's, let's say from this formula here, if we turned every A into a B and turned every B into an A, we'd get probability B and A over probability A, which is exactly the same thing as what you have here. So while something like a probability of A is called a prior probability, a conditional probability is also known as a posterior probability, which is a revision of the prior probability using additional information. All right, so this looks like the same example as before. We want to find the probability that a student scores over 600 given that they completed the prep class. So if we're going to use the formula, first we would find the probability of A and B, which is 22 students total scored over 600 out of 250 students total. 22 over 250 is 0.088. The probability of B, that a randomly selected student completed the prep class, there are 70 students that completed the prep class over 250 total, which is 0.28. So if we use our formula, the probability of A given B is equal to the probability of A and B divided by the probability of B. We get 0.088 over 0.280, which comes out to 0.314, which is the same answer that we got when we did it the other way. All right, independence. Two events are considered independent of one another if the occurrence of one event has no impact on the occurrence of the other event. It doesn't make it any more or less likely. If the occurrence of one event does affect the occurrence of another event, then the events are called dependent. Now, they might say this on another slide, I can't remember, but I want to caution you that independent does not mean the same thing as mutually exclusive. They are completely different. All right, independent sort of means unrelated. The two events are unrelated to each other. So think event A is the probability, or event A is a randomly selected student is a math major. And event B is randomly selected student has brown eyes. All right. As far as I know, it is not any more or less likely that a person with brown eyes will be a math major than, you know, people in general. So those two events are probably independent. However, they are definitely not mutually exclusive, because there are definitely math majors with brown eyes. I'm one of them. All right. Okay, so those two things are not the same thing. I don't want you to get them mixed up. All right, the formula for determining if events A and B are independent looks like this. The events A and B are independent if the probability of A given B is equal to the probability of A. And that kind of makes sense if you think about what independent is supposed to mean, all right? You know, I ask you, what is the probability that event A occurs? And I say, but I'll give you a hint, event B has also occurred. Well, if the events are independent, then that hint is not going to be any help, because the two events are unrelated, okay? If these two probabilities are not equal, then that means the events A and B are dependent. All right, so in this example, we'll look at event A, which is a student gets a grade of 80% or better. Event B is the student is interested in the subject. So out of 200 students, we have 114 of them are interested, 86 are not. 110 students got 80% or better, and 90 students did not. So if we found the probability of A given B, and we'll do that the first way we did it, which is the easiest way if you're working from a contingency table. Just pretend again that, get my pen out here. Pretend that the students who are interested are your whole sample space. So out of those 114 students, 72 of them are interested, which means the probability of A given B is 72 over 114, which is about 0.632. However, the probability of A, which is probability a student gets 80% or better, is 110 out of 200. That comes out to 0.55. Since those two numbers are not equal, that means the event student gets an 80% or better and the student is interested in the subject are not independent. See, if the student is interested in the subject, it's a little bit more likely that they will score 80% or better, which kind of makes sense. All right, that brings us to the multiplication rule. The multiplication rule is used to determine the probability of the intersection of two events occurring. So the addition rule is used to find the union, the probability of the union of two events. The multiplication rule is used to find the intersection, the probability of the intersection. So here we have the formula for the multiplication rule. And again, they put for dependent events in bold, but these formulas will work all the time. They'll work even if the events are independent. It's just that if you know the events are independent, then you can make these formulas a little simpler. Now, this formula we already know. This is the formula for finding conditional probability. If you multiply both sides by probability of B, you get the multiplication rule. Sorry, I'm trying to find my pen again. All right, so this is actually the formula for the multiplication rule. And it also comes in another form. All right, if you take the other version of the conditional probability formula and you multiply both sides by probability of A, then you get this version of the formula. So it's sometimes a little tricky trying to decide which version to use. You have to decide based on whether you have the probability of A given B or the probability of B given A. And sometimes you have to think about that for a few seconds. All right, so let's see what we have for an example. Event A is rain is forecasted. Event B is carry an umbrella. So if the probability that rain is forecasted is 0.3 and the probability that you carry an umbrella given that rain is forecasted, and we want to find the probability of A and B. All right, so how do I know that I should use this version of the formula? It's because they gave me the probability that I carry an umbrella given that rain is forecasted. And they're calling carry an umbrella event B, rain is forecasted event A. So they're giving me probability B given A. All right, so I have to use the second version of the formula. All right, so that's going to be probability of A times probability B given A. 0.3 times 0.9 is 0.27. So there is a 27% probability that it will rain and you will carry an umbrella, that both of those things will happen. Now, if your events happen to be independent, then those formulas that we were just talking about, in particular, I would say this, well, no, it's either one. Those formulas that we were just talking about simplify to probability of A and B is equal to probability of A times probability of B. And that is because if your events are independent, the probability of B given A is equal to the probability of B. So what we were looking at earlier looked like this. Instead of probability B, you had probability B given A. All right. So if we know that our events are independent, then we can just replace probability B given A with probability B. And then when multiple events are all independent, the probability of them all occurring is simply the product of their individual probabilities. The probability that A1, A2, A3, blah, 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 and AN all happen is equal to the probability of A1 times the probability of A2, times the probability of A sub n. All right. So let's see. We're going to convert these table frequencies into probabilities by dividing each number in the table by the total number of observations. So we're looking at frequency of customer satisfaction by entree type. 80 people ordered meat, 120 people ordered fish, 170 people were satisfied, 30 people were not. All right, so if we want to make that into a probability table, we'll just divide all of these numbers, each and every one of them, by 200, and that gives you what you see here. Okay, so let's see, what are we doing now? Sorry, okay. So the probability of customer satisfaction by entree choice. In yellow here, you have your joint probabilities, which are your intersections, like the 0.35 is the probability that the person ordered meat and was satisfied. And then down here in orange, you have your simple probabilities. So this one here is the probability that the customer ordered fish. Your conditional probabilities, so A given C, that would be the probability that the person was satisfied given that they ordered meat. Using the formula, you get probability A and C divided by probability C. Here is probability A and C. Here's probability C. 0.35 divided by 0.4 is 0.875. And they're also showing you the probability the person was satisfied given that they ordered fish, the probability that they were not satisfied given that they ordered meat, and the probability that they were not satisfied given that they ordered fish. All right, so this is called a decision tree or just a tree diagram. And I'm going to be using one of these a little bit later to simplify something that I think is going to sound kind of complicated at first. So the idea is that you pick a customer and first note whether they're satisfied or not satisfied. The probability that the person is satisfied is 0.85. The probability they're not satisfied is 0.15. Now, if the person was satisfied, then the probability that they ordered meat is, okay, they didn't fill in that part. But what they have over here is the probability A and C, probability they were satisfied and they ordered meat is 0.35. The probability that they were satisfied and ordered fish is 0.5. The probability they were not satisfied and ordered meat is 0.05. And the probability they were not satisfied and they ordered fish is 0.1. Notice that these four probabilities add up to 1 because they represent the entire sample space. So remember that mutually exclusive events are events that cannot occur at the same time. Using our previous example, events A and B, which are customer is satisfied and customer is not satisfied, they would be mutually exclusive events because a customer cannot be both satisfied and unsatisfied at the same time. So that means probability A and B equals 0. Likewise, events C and D are mutually exclusive because the entree cannot be both meat and fish. It has to be one or the other. So mutually exclusive events are automatically dependent. You know what? I'm going to kind of skip over this slide. I don't think this is all that important. Two events cannot be both independent and mutually exclusive. Yeah, we'll skip over that. Okay, so now I believe we are at Bayes' theorem, correct? Yes. So the goal is to develop a rule to calculate probability A given B from information about probability B given A. Suppose two events have prior probabilities, probability of A1 and probability of A2. Again, these are called prior probabilities because they are determined without any other information. And suppose that A1 and A2 are mutually exclusive. If the conditional probabilities, probability of B given A1 and probability of B given A2 are known, then we can find the probability of A1 given B by using this sort of scary looking formula. And so I'm going to go on record now and tell you that usually when I do a Bayes' theorem problem, I don't even use this formula. What I do is I draw a tree diagram. So I'm going to show that to you here in just a couple minutes. And then what looks even worse, the formula for Bayes' theorem for n events. So we were just looking at the formula for 2 events. So in this case, you would have A1, A2, A3, up to AN that are all mutually exclusive. And so for each one of those events, probability A sub I given B, you could find it using this formula, okay? That is supposed to be a ... there. So I've noticed sometimes the ... gets replaced with a little box. Okay, So we'll look at this example using the formula. By the way, this is the last example. I know this has been kind of a long video. So we'll look at it the way they did it first, and then I'll show you how you can do it using a tree diagram, which I think you might find a little simpler. So PNC Bank classifies its credit card customers into 3 categories by their credit scores. 25% of customers have a credit score less than 600. 45% have a credit score 600 to 700. And 30% have a credit score more than 700, okay? So notice that those 3 probabilities add up to 1 because your credit score has to be one of these 3 things. And let's define event B to be the customer is late on their credit card payment. And suppose the following historical information is known. Customers with credit scores of less than 600 are late with their payments 40% of the time, which means the probability B given A1 is 0.4. Customers with credit scores between 600 and 700 are late with their payments 10% of the time, which means probability B given A2 is 0.1. And customers with credit scores of more than 700 are late with their payments only 5% of the time, which means probability B given A3 is 0.05. Suppose PNC Bank wants to determine the probability that a customer has a credit score of less than 600 given that they are late on their credit card payments. So that would be the probability of A1 given B. So using the formula, which would look like this, this is what you get. So, you know, easiest thing might be to look at those previous 2 slides, you know, write down all that information and then put all those numbers where they're supposed to go. All right, and what you get is that there is a 62.5% chance that a late payment is from a customer with a credit score of less than 600. So now I want to show you what I think is the simpler way to do this, and then we will be done with this section. All right, here it is. I went ahead and did it ahead of time. So I made a tree diagram. So we're going to start here. And we're going to pick a customer, and there's a 25% chance that that person has a credit score less than 600, a 45% chance that it's between 600 and 700, and a 30% chance it's more than 700. Now, if the person has a credit score less than 600, there is a 40% chance that their credit card payment will be late, which means a 60% chance that it won't be late. If the credit card payment is made by a person with this credit score, between 600 and 700, there's a 10% chance it's late and a 90% chance it's not. And then if the payment comes from this group, there's only a 5% chance it's late and a 95% chance it's not. All right, so moving down here to the formula. So if I wanted to find the probability of A1 given B, just using the conditional probability formula, you get probability A1 intersect B divided by probability B. Now I'm doing this without even thinking about the Bayes theorem formula, okay? So the probability of A1 intersect B, that is this event up here, right? The probability that they have a credit score less than 600 and their payment is late. So that's 0.25 times 0.4. So that's going to go right here. Now probability B is separated into 3 different categories. So this is the probability that the payment was received late. All right, so we have to break that up into it was late and it came from a person with a credit score less than 600. It was late and it came from a person between 600 and 700, or it was late and it came from a person more than 700. So if you break probability B into those three separate outcomes, then you can just write these numbers here. And you get exactly the same thing that you would get using the formula. I just think that this is easier to wrap your head around than that formula. Even I don't like that formula. And I'm a person who likes formulas usually. All right. So that is finally going to do it for section 4.2, and we'll see you next time.